Okay, welcome back. Last video we have seen we had a recap of what we have done. We have seen the unique solutions for each of these boundary value problems for the wave equations, and now we have considered a non-homogeneous wave equation with the initial data, for which we need to find a solution. So one can find by directly integrating out. So that's what we will do. So uniqueness is also shown by one can show the same energy argument is true even for this non-homogeneous equation with the initial data. So uniqueness of the solution is guaranteed, and you have only need to find work out the solution. So we will see that in this video. So let us take this non-homogeneous equation. Wave equation is right hand side. You have a forcing which is non-zero, h of x t is non-zero. You have a external force and you have this initial data. This is for every real line. On the full real line you have this. One needs to find the solution. So how do I find the solution? So what we do is you consider this as a partial differential equation. So like just find the general solution. How did we do? We make use of this classification. So try to find the normal form for this wave equation. So how did we do this? If you bring in the new variables, xi equal to x minus ct and eta equal to x plus ct. If you consider these two new variables, then you have this equation, this wave equation becomes simply you have u xi eta minus 4c, right. If you just go back and see, as going to become minus 4c square u xi eta equal to h of x t. X and t you replace with what happens, x and t, x equal to xi plus eta by 2 and t is xi minus eta by 2c. So that is what is your h of simply x and t you can replace with xi and eta. So finally you have something like h of xi and eta. So xi h is now in terms of xi and eta. So this is what it becomes. Okay. So wave equation becomes this. Okay. So this we will try to integrate directly. So this is what we will do. So we will try to see how to integrate this equation so that you can find your u xi eta. So what is your initial data? Initial data is u x0 equal to fx. Okay. So I need to, so this is what is your equation. So you want a zero boundary. So 0 initial conditions. If you want, you have to break this problem, actual boundary value problem, into two problems. Okay. So let us do this first. So let us break this problem into decompose the boundary value problem into, because this is a linear problem, so you can reduce into two problems. So let into two problems. So let u of xt be u1 of xt plus u2 of xt. So where u1 satisfies the homogeneous equation. Okay, let's choose this. So that is u1 tt minus c square u1 xx equal to 0, and then initial values. So u1 at x0 equal to, you take the full initial values, this takes full initial values, u1t at x0 is gx. So from this problem I have given for u1 this initial data, and the non-homogeneous part I make it 0 for this u1. So this is for u1 problem, and for u2 you have u2 tt minus c square u2 xx equal to h of xt. So that when you substitute u1 plus u2, okay, you apply utt is u1 tt plus u2 tt minus c square uxx, that is here minus c square u1 xx minus c square u2 xx. So this will be 0 because of this, and this will be h of xt. So finally this is satisfied. Equation, non-homogeneous equation it becomes. Okay. and then if you now the initial data becomes u2 at x0 is you have to give 0 because u at x0 is fx. This fx is u1 has already taken, so u2 has to be 0. Okay. Similarly, u2t at x0 has to be 0. So, I decomposed the actual non-homogeneous boundary value problem, initial value problem. Okay. So, actually it is an initial value problem, non-homogeneous initial value problem into decomposed into two problems. One is homogeneous wave equation with the initial data. This is what you have D-Alembert solution. So, u1 of xt is D-Alembert solution, D-Alembert's solution. So, you know that this solution is D-Alembert solution. This is what I should find out. So, we need to find u2 of xt. This I do not know. Okay. This we have not seen so far. So, to do this, what we made use of this new variable xi and eta. So, xi and eta. So, this is what is your problem now. So, your problem is not actually non-homogeneous now, non-homogeneous with non-zero initial data. What you have is this non-homogeneous equation with 0 initial data is actually your problem. That is how you decomposed. So, with this new xi equal to x minus ct, eta equal to x plus ct, with xi is this, eta is this, we can see that u2 of xi eta, u2 xi eta derivatives minus 4c square equal to h of xi eta. This is what it becomes for this non-homogeneous wave equation becomes this. Okay. The non-homogeneous wave equation becomes with these new variables. So, this is simply normal form, putting them in the normal form in the new variables xi and eta we have seen. So, while doing the classification we have already seen that how to make this one. So, this is what you will get. So, this is what you have to integrate. So, you want to integrate to find this u2. How do we do this? So, you have this you consider this initial data. So, initial data is u2 at x equal to 0, u2 at x0 equal to 0, that is the initial data, right. u2 at x equal to 0 is the initial data. So, this implies u2 x at x0 is also 0. Okay. So, you simply differentiate with respect to x u2. So, you will see that this is true. Now, what is the other initial data? Initial conditions are this, u2t at x0 equal to 0. Okay. So, this is the other boundary condition. So, now u2 is a function of xi and eta. Okay. So, what is the u2t of xi and eta? So, u2t is u2 xi dou xi by dou t xi t plus u2 eta eta t. Okay. So, this is equal to what happens. So, xi t is minus c u2 xi and here plus c, eta t is plus c, that is u2, this is minus plus. Okay. So, you have a c u2 eta. So, that is what is your u2t xi eta. Okay. Now, from this xi and eta one can find x, xi is x minus ct, eta is x plus ct. So, you have xi plus eta by 2 is x, t is xi minus eta by 2c. So, t equal to 0 means xi equal to, t equal to 0 means xi equal to eta. Okay. So, that is what you have to find out. So, when you want put t equal to 0. So, u2 at t equal to 0, u2 at x0 equal to 0 is nothing but u2 at xi equal to 0. Okay. Because I put the eta equal to xi, so this is what is the condition in the new variables. u2 xi is 0. So, that is what is this first initial condition. And second one, so the second one is this, second one will give you second boundary condition, that is u2t time derivative of x0 equal to 0 will give me, that means this is equal to 0. So, they have u2 xi minus u2 xi at x0 means you have to write xi, but eta is equal to xi at t equal to 0 minus u2 eta at xi equal to 0, that is what is this initial data. Now, you also know this u2x at x equal to 0. What is u2x? You do the same way like u2t. If you do for u2x derivative at x0 or xi eta is u2 xi x. Now, you have to take xi x plus u2 eta x. So, eta x xi x is 1. So, you have u2 xi plus u2 eta. So, this means u2x at x0 is nothing but u2 xi, the derivative at xi plus u2 eta at xi equal to 0. Okay. So, this is equal to 0 means this is equal to 0. Okay. So, consider this and this, their sum is 0 and difference is 0, that means each of them is 0. So, u2 xi equal to 0 is also true for u2 eta xi is also 0. Okay. And you also know that u2 at xi is also 0. So, you have these are the initial data. Initial data becomes this is your initial data, initial conditions in the new variables. Okay. What is the equation becomes? Equation becomes this. Equation is this and your initial data is this. Now, try to integrate. Now, if you try to integrate this one, you simply get u2 xi eta is u2 xi eta equal to minus 1 by 4 c square h of xi eta. This is what is this? This you have to integrate. So, your full x is full real line and t is positive. This is your x. Okay. So, if you want solution at some point, let us say some x naught t naught, you really want this one. Okay. So, we have to define something like a domain of dependence, domain of independence. So, if you look at the D-Alembert solution u x t u x naught t naught, if I write u x naught t naught, that is actually dependent on half of the initial data, that is f at x naught plus c t naught, xi is whichever. Okay. X plus c t naught plus f at x naught minus c t naught. So, okay, this is half of this plus 1 by 2 c integral x naught minus c t naught plus x naught plus c t naught into the other initial data, its velocity, that is g of x dx. So, this is what you have. This is what is the D-Alembert solution if in the full domain. So, if you want this solution, and what is this x minus c t x plus c t, x naught minus c t naught. So, this is x naught minus c t naught is see, this is the line, this is the line. If you take this cuts at x naught minus c t naught, if it is 0, there is a parallel line cuts here. This is the line that passes through origin, that is x naught minus t c t naught equal to 0, and this is something else, some non-zero, and the something similar parallel lines will go even this side. This is x naught plus c t naught line. So, these are your characteristics. This is your xi. So, xi naught equal to, so if you fix your xi equal to constant, okay, xi equal to xi naught, this is your xi naught in xi eta plane. So, if you take this is actually this is your xi and this is your eta, okay. So, this is the line, xi is constant. So, you have xi is constant means xi is here, okay. So, this is the line xi equal to constant. So, xi equal to constant is this line. So, you have xi equal to constant means, so this is your eta axis, okay. So, this is your eta, this is your xi. So, this is how it looks. So, this is the xi eta. So, you have this is your eta. So, this is equal to some eta naught. So, x naught t naught, this point in the new variables xi naught and eta naught, okay, and you have this xi naught and eta naught, okay. And what is this line? This line, so parallelly if you look at this x minus c, x plus c t equal to 0 will give me this line, okay. So, this line is exactly xi equal to eta. This line is actually xi equal to eta. So, if you want a solution here at x naught t naught, from this D-Alembert solution you can see that depends on the initial data here. For that matter, any point inside this triangle actually depends on this data. So, this is the influence solution for the solution. This is the domain of influency. This is the domain of influency as a triangle area, and this is the domain of dependence for the solution. So, this is actually depending on initial data only here, if you want here, or any data inside any solution at any point inside, you need only a data maximum here, okay. And this is because it you get every solution within this based on this. This is the influence of for the solution. This is the domain of influency. So, this is the domain you consider as delta, over which you are going to integrate, try to get the solution. So, you will see how we do this. So, we are going to integrate over this domain in the xi eta variables, okay. So, if you do this, you will try to redraw this picture. So, if you do that, so what you see is this is the triangle what you have over which you want to integrate. So, this is your xi naught eta naught, x naught t naught correspondingly that takes you to the new variables xi naught eta naught, and this is your xi naught. Xi naught eta is also same. So, xi naught, okay. Here this will be eta naught, and here in this is the line on which is xi equal to eta. So, eta naught is same as eta naught. So, this is what is your solution. This is what is the in this what is your coordinate axis is this, okay. So, this is parallel to this is your eta line, and this is parallel to this line. So, this is your xi line. So, within this you want to integrate this one. So, first to do that, so you integrate from xi naught to eta naught as your xi naught to eta naught as your d xi, okay, and you integrate from this is your xi equal to eta. So, you do it from xi to eta naught with your d eta, then you are actually doing integration over this triangle, okay. So, closely observe, you see this, this is from, so if you actually see this one, okay. So, xi is, this is your eta, let us say this is your eta line, eta is from xi naught to eta, okay. So, xi is, this is your xi line, xi is from xi naught to eta naught. So, I integrate from xi naught to eta naught, and you have what is your eta? Eta goes from, eta is from xi, from this line to up to here, that is eta naught. Okay. So, if you will try to integrate that, so first you integrate first xi to eta naught. So, integrate from xi to eta naught to get. So, x naught t naught in the new variables xi naught eta naught, and this line x minus c t naught equal to xi naught, that is xi equal to xi naught, and this is xi equal to eta line, and this line, that is x plus c t naught equal to eta naught, that is eta equal to eta naught, because your xi eta are these are the variables, xi is x minus c t, eta is x plus c t. So, once you have this, you just have to integrate this equation, you integrate. So, what is your xi? Xi is you are in this coordinate system, xi and eta. Xi is xi you have to integrate, xi is actually varying from, so this is the line, this is the line, this is the xi line, xi equal to xi line, that means this is your eta axis. So, eta is running from xi naught to eta naught. So, eta you have to do it from xi naught to eta naught, and xi is running between this line to this line. So, this line is xi naught to this line is xi equal to eta. Okay. So, for that reason, so first you integrate this, so this double integral. So, double integral over this delta. So, double integral over this delta is basically any double integral. So, this is d xi d eta is actually, one can see that this is the line. So, this is your eta axis you just varying. So, this is from xi naught to eta naught. So, eta is running from d eta running from xi naught to eta naught. Okay, this is constant. Now, xi is between this line to this line, so that you go up to here. So, xi eta is actually xi naught means this line. So, this line to this line. So, this line is eta equal to eta naught. So, eta equal to xi naught is this line, okay, that is parallel to the xi axis. So, eta equal to xi naught to eta equal to eta naught, that is d eta. So, that is integration from this, and then if you want integral over this delta, so you should take between this line to this line, that is xi. So, the xi is d xi. So, this d xi integral should be from xi naught to xi equal to eta. So, xi naught to eta. So, this is what you have to do. So, we will try to, so any integration goes like this, integration over delta is as an iterated integral is this. So, now we try to integrate this this equation, now starting with xi. So, we integrate from xi naught to eta with respect to xi to get. So, I will just remove this. So, if you integrate that above equation from xi naught to integrate from xi naught to eta with respect to xi. So, what you get is integral xi naught to eta d xi. So, u to xi eta of d xi equal to minus 1 by 4 c square integral xi 0 to eta h of xi eta d xi. I am doing it with respect to xi. So, this becomes u2 of xi eta. So, u2 of u2 eta of xi eta. So, that is xi you have to replace with eta xi minus eta xi eta. So, in the place of xi I put eta. So, you have already have eta. So, u2 eta of eta minus u2 eta. Now, it is at xi I have xi naught. So, xi naught eta. So, this is what after integration. So, this will be dou xi of u2 eta. So, the u2 eta at xi equal to eta is this, and u2 eta at xi equal to xi naught is this. This is equal to the right hand side. So, this 4c square xi naught to eta h of xi eta d xi. Now, if this one I can integrate. So, now I know that u2 eta of eta eta is also 0. So, this is what you get, u2 eta of if this is same, that is 0, okay, that is the condition. So, u2 eta of xi xi or eta eta both are same. So, okay, so that is 0. So, xi equal to eta. So, that is eta eta means xi equal to eta. So, that is this is also 0. So, this is actually 0. So, this means one can see that this is same as u2 eta of xi xi xi, this is xi eta. So, both are same. So, when both are same, this is also 0, okay. So, both are same, these are equivalent, okay. So, if I use this, this is what it becomes, this is 0. So, now you integrate this from now. So, now your integration from eta. So, eta is if you integrate eta variable from eta equal to xi naught to eta equal to eta naught. So, this between these two lines if you do, that is a triangle. So, if you now do this from xi naught, eta is from xi naught to eta naught, this is with for this full integral, that is 0 d eta equal to, now if you do this from this side also xi naught to eta naught d eta. So, this is the integral. So, this is anyway 0. So, this quantity is 0. So, you can remove this. So, you have a minus. Now, you can write u2, this is now this is dou u2 by dou eta integral. So, you have finally what remains is u2 at xi naught eta naught. So, u2 at xi naught eta naught minus plus u2 at xi naught, and you have a xi naught here. So, this also 0, this we know that it is 0. So, this is equal to 1 by 4 c square. This double integral, this iterated integral right hand side is nothing but the integral over this delta region h of xi eta d xi d eta, okay. So, this is what you get. So, u xi is finally, so you make it plus, both sides if you cancel minus you get plus. So, finally, you end up so this is 0. So, we can remove this. So, this is nothing but simply this is what you get, this is the u2 solution at xi naught eta. Okay. The second solution is u2 of xi naught eta naught is 1 by 4 c square over this delta region h of xi eta d xi d eta. So, what is the delta region? The domain of influence, that is the domain of influence, that is this is the domain. In the old variables, you want to convert this into old variables. So, that is xi naught eta naught becomes x naught t naught, and then this part becomes x naught minus c t naught 0, and this becomes x naught plus c t naught and then 0, this points, okay. These are the 3 points. So, if you write this 4 c square double integral over this delta, now I just changed, I go from xi eta to xt variables, okay. So, if I do this, so d xi d eta, the area element here is a Jacobian times dx dt, and so that this becomes h of xt, okay. This is what it becomes, and so that this is actually u2 of x naught t naught. So, in the old variables, this is what it becomes. What is the Jacobian? The Jacobian is modulus of the Jacobian is first of all Jacobian is the determinant of xi x. Xi is actually x minus ct, eta is x plus ct. So, xi x is 1, xi t is minus c, eta x is 1, eta t is c. So, you get what you get is c plus, so you have 2c. So, what you are left with is 1 by 4 c square. So, 2c if you replace, this is over the delta in the xt plane, this is actually t this is actually in the x, in the xt plane, this is what you have. So, this is your domain D, this is your delta D, okay. H of xt, now this is 2c dx dt. So, this is still the double integral. So, 2c goes, what you are left with is 4c squares. So, you have 1 by 2c double integral over this delta. This double integral over delta you have to write it as a iterated integral. So, that we will see how to do this. So, how do we do this? So, you need, so if you want to do this, t is running from 0 to t naught. So, you fix your t equal to t naught, okay. Between 0 to t naught you fix your t, then your x should go from this point to this point. So, that means from this line to this line, okay. So, this is how you are doing, you fix this point and you are going from here. So, for every fixed point you just fill this domain, okay. So, for that you need a equation of this line. So, equation of this line is, you can find this equation of this line, x minus x naught, actually y minus y naught, that is t minus t naught equal to, so t naught divided by x naught minus x naught plus c. So, you have a c t naught into x minus x naught. So, equation of a line passing through x naught t naught, and you have 2 points are given. So, from that you can calculate the slope, okay. So, what you are left with is, the equation of this line is x equal to ct in the xt planes, you have ct plus c times minus ct naught. So, ct minus ct naught, and then you bring this x naught the other side. So, you have plus x naught, okay, x naught plus c times ct minus ct naught. So, if you do the same thing here, so the equation of this line is, if you do the same thing, so t naught, and what you are left with is this difference, the slope is t naught minus t naught divided by x naught minus ct naught. So, only difference is minus here, okay, for this line. So, in this case you have x equal to minus x naught first of all minus ct plus ct naught. So, these are the equation. So, if I write this as an iterated integral, what you have is 2c. Now, this is, now I have 0 to t naught dt. Now, this integral, other iterated integral is running from x is from x naught plus c times t minus t naught to, right, to x plus x naught minus c t minus t naught, okay. So, the difference is, am I doing right properly? So, we have t0 minus this, that is fine, okay. That is your h of x t dx. Dx, x is running from this to this, okay. So, what you have is, now you can change the dummy variables, x naught and t naught you can write it as x of t. So, you can write as x of t, so that your dummy variable x and t you can replace with something else. So, you have 1 by 2 c 0 to t, t I can write it as d, so let us say t I am replacing with t naught, okay, t naught I am replacing with t naught I replace with t, and t naughts I am replacing with t naught, okay. So, you have x naught I replace with x. So, x plus c times c naught t naught minus t, okay. So, that is minus t minus t naught to x minus c times. So, it is going to be plus because the t is t naught and t naught is t. So, we have finally t minus t naught, okay. H of x is simply x naught. So, I am replacing x by x naught by x, comma t naught d x naught. So, x naught and t naught are dummy variables. So, if I change this to t naught by some s, what you have is t minus s, here t minus s, okay. And you do not want x naught, so you write it as some y dy, x naught you replace with y, that is all, that is what you have, okay. X naught you replace with y, so that is only dummy variable, so that is what you have. Okay. So, nowhere else you have x naught, so you do not need to replace. So, this is your second solution, solution of the second problem, okay. This is the solution of a second problem that is for u of x2, u2 of xt. So, what is the solution? The solution is now so one is the D-Alembert solution, that is u1 plus u2. So, what is u1? u1 is the wave equation with the initial data f and g. So, you can write together the solution of the problem is now. So, you can write u of xt, original problem is u1, that is half times f of x minus ct plus f of x plus ct. This is the D-Alembert solution. So, plus 1 by 2 c integral x minus ct to x plus ct g of s ds. This is my u1. Now, plus u2 is this part. So, that is 1 by 2 c integral 0 to t x minus c times t minus s to x plus c times t minus s. This is the forcing term h of ys dy ds. So, this is your this is the required solution. This is the required solution of the problem, non-homogeneous problem, okay. So far we have constructed, this is the solution, we have constructed by just splitting into two problems. One is the D-Alembert's problem, other one is non-homogeneous problem. Just by integrating the equation we just found this u2. So, this is how we constructed the solution, and by the same energy argument we can see that the solution of this problem, the original problem for u, is having a unique solution. So, that means this is the solution, okay. So, this is the unique solution, this is the unique solution for the problem, okay. Same energy argument that we have seen earlier you can also apply here. Consider two solutions and take the difference, and it satisfies you take the difference, it will satisfy some other boundary problem. Now, we use the energy argument to show that the W1 is equal to the W equal to 0. So, this is how you solve the non-homogeneous equation, okay. So, in the next video we will, so far we have seen only two-dimensional one-dimensional wave equation and its problems, okay, initial boundary value problems for the one-dimensional wave equation, okay. So, this is how we solve a non-homogeneous equation for the one-dimensional wave equation, okay. So, this is the solution that is the sum of both. We split the problem into two problems, one is the D-Alembert's problem, other one is non-homogeneous problem with the what is exactly we have is the second solution is non-homogeneous wave equation with zero initial data, okay. That is what we find just by integrating over this xi eta domain, so over this domain of influence region. So far we are solving only wave equation in one dimension. So, you can also find we can also solve a two-dimensional wave equation, okay. So, that we will see what is the two-dimensional wave equation in the next video. Two-dimensional wave equation, it is actually same equation, only thing is spatial domain will take the plane region. So, that is utt, earlier minus c square uxx, now you have uxx plus uyy equal to 0. So, xy belongs to R2 and t positive, What we do is we do not solve in the general full domain. So what we do is we consider we can solve certain problems in some domains, that means let us consider some circular domain. So 0 to r, so because it is a circular domain you can reduce into polar coordinates, you can reduce this equation into polar coordinates r and theta variables and look for solutions, radially symmetric solutions, that means a solution u of x, y and t, that is in the polar coordinates this will be u of r theta t, you look for solutions only radially symmetric, that means should depend on, it does not depend on theta, that means the solutions are only u of r of t. Okay. If you look for solutions like that, whatever solution is known, if you are vibrating, if whatever is a vibration along at theta equal to 0, it is repeated all along theta between 0 to 2 pi. So that means radially symmetric vibrations you can, if you look for as a solution, we can actually solve this 2-dimensional wave equation using separation of variables. So you can actually bring in Bessel equation, okay, that you have learnt in the earlier videos. Okay. So using the best solutions of the Bessel equation we can find the solution of this vibration of the drum, so for all times. Okay. This is what we will see in the next video. Thank you very much.